the cloud. Hi, everyone. Thank you for joining us today. Before we get started, I want to bring your attention to Exceed's Code of Conduct. Everyone is generally on good behavior, but if you do observe any inappropriate behavior, please let us know by reporting it to exceed.org/code of conduct. Exceed is also trying to be sensitive to terminology used in these training sessions. So if you do observe any inappropriate terminology or materials, please send an email to terminology@exceed.org. I will include some quick housekeeping rules. If you have any questions or comments, as Mary mentioned, please post them in the chat. We will do our best to answer them at the very end of Mary's talk. And I do ask if you could please keep your video and mic off during the session to avoid any interruptions or network issues. And with that, I will stop sharing and let Mary take over.
Okay, so I will start sharing. Can you all see my screen with my PowerPoint slide on it?
Yes, I can.
Okay, great. So there's the webinar. Right, so this is the Expanse webinar. I'll go into screen share mode and also display mode. Okay, can you guys see my cover slide?
Yes, we can.
Okay, great. All right, so here we go. I am Mary Thomas. I'm a computational scientist and physicist by background. And yeah, I got my PhD in computational fluid dynamics, ocean modeling. And I'm also the HPC training lead at SDFC. So working with Cindy and Susan and the user services people, we spend the year putting together, we hope, what we hope are very useful webinars, workshops, and institutes. And I'll show some links. You can go to the same web page where you found the link to this webinar and take a look at what we've got coming up. And we also have been working on building a catalog showing events that we've had in the past. And our goal is to have every event have some persistent material. So you can go back and find the previous webinar, look at the recording, download the talk, and if there's any training material associated with it, there'll be a GitHub repository. For example, today, this will link to a repo with very basic examples for you to run code on Expanse to get you going. So with that, I'll move on to my outline. Let me try and get this navigation thingy out of the way. It won't let me take it off the screen. Okay, so we're covering a lot of material today, and it says at a very basic level, I hope. And if not, we can send you to some other links. But we'll just look at what's required to even get logged onto the machine. The assumption is that at the Expanse 101 level, this is very basic. You guys are new, maybe new to HPC. Maybe you have a fantastic application or scientific domain you're working in, and it's too big for your laptop, it's too big for your local cluster. And now, unfortunately, or fortunately, depending on your point of view, you need to run your job on a big machine. You need more memory, you need more cores, you need to scale your job up or something like that. But at some point you have to come onto a bigger system. And we're really sensitive to the fact that this is challenging and it's hard if you're very, very new. And even if you aren't new, you might be coming to a new machine that's somewhat different, like Expanse, and you still have to learn the basics of where are the files located, what libraries do we have, how do I compile on Expanse. It's always a little bit different, every HPC system around the country and the world. They're all a little different. And so learning how to run on that environment is important. And that's the goal of this talk. I hope by the end, you have some idea either of the scope of learning you need to approach and you need to do to run jobs, or the little bits that you need to pick up and get going so that you can continue running your job. So getting going, let me make sure. Okay, so there's some basic information. We have a user guide. And you need to have an account. If you don't have an account, you need to go to the Exceed allocation. If you need to have an allocation, you go to the request system. You can get a trial account very quickly on Expanse by going to the portal. Anybody can make a portal account with Exceed, and then you have to have some allocation or permission or need to get onto a machine where you're actually running jobs. But at this point, you get started in the process of figuring out where you might run your jobs. And then we have a repo for this particular presentation. And we also have the link to the training event. So here we're just going to do a quick overview of Expanse. That's my background picture. This is the cluster consists of about 13. These are racks, if you know computer hardware, sorry, and we call them scalable compute units. There's 2 rows of these racks, and the bright lime green lights is actually illumination of the cooling system. Because we're compressing so much hardware into such a small space, the current generation of commodity computers now involves liquid cooling. My son has a liquid cooling machine on his desk in his room. So liquid cooling is becoming more common. And so this is Expanse. It's the theory is computing without boundaries. It's a 5 or more petaflop system with large data services and high-speed networking. And the vision of Expanse is an extension of Comet, which is that we're serving what we call the long tail of science. There's a lot of people who run jobs that just require a few thousand cores in this day and age. There are some jobs, projects that need hundreds of thousands of cores, and those are larger scale systems, and there's several of them funded by NSF, but we're a different focus. Our goal is to have a lot of people running these medium-sized jobs and getting them done quickly. And so Expanse was designed for that. So we have what are called these scalable compute units, and I'll describe them in a moment. There's 13 of them. Between them, we have 728 standard compute nodes, 52 GPU nodes, and 4 large memory nodes. And we have a data-centric architecture with 12 petabytes of storage, 140 gigabit per second network, very high-end resources. We have plans and capability to integrate remote cyber infrastructure services, anything from a remote cloud computing resource to remote data. We're trying to integrate, we have OSG integrated into Expanse, and then some innovative projects that I'll talk about briefly, just to give you an overview. Composable systems, high throughput computing, gateways. We have a lot of large scale gateways running on Expanse, interactive computing, containerized computing that's becoming very, very common, and cloud bursting. So this architecture, to burrow in just a little bit more, we have 13 of these scalable compute units. Excuse me, 720 nodes, 93,000 plus cores, 200 terabytes of RAM memory, and 208 V100s, 4 terabyte memory node, large memory nodes. It's a very large system. We have Ceph object storage, and we have a Lustre file system, and it's all liquid cooled. So these scalable compute units, we just got funding for a couple more, and so we're going to have even more of these. The idea is that everything you need to run the kind of jobs that we're targeting Expanse towards, they should fit on one of these SCCUs, even if you're doing hybrid CPU, GPU acceleration, so that it might run faster. And so it's sort of self-contained. Not that you couldn't do multiple SCCUs, we also allow that, but it'll be optimized for you if you can fit things on one of these SCCUs. Okay, so it's designed for this long tail of science. And so burrowing down in, this is what you would think of as a compute rack. Like I said, we call it a scalable compute unit. And it's got multiple nodes, 14 of these nodes, and each node has 4 CPUs on them, and also 4 NVIDIA V100 nodes. So when you get on one of these racks, you have access to all of this hardware. And then we have a high bandwidth connectivity fabric that integrates the SCCUs to object storage and performance storage, Lustre file system, and then external networks out to the whole, NSF funded research computing infrastructure across the nation and internationally as well. So a little quick overview of the AMD, the EPYC processor is, it's a very unusual processor. It's a pure NUMA. What we've got are these, there's 8 of these complex dies, CCDs, and they each have some local memory, and then they have a shared memory infrastructure. And there's multi-channel memory channels, so you get high bandwidth IO if your job, especially if your job is running on one of these cores, on one of these CCDs. And then there's DDR4 memory, PCI bandwidth memory of transmission lanes, and the Zen 2 cores share cache. So you have a lot of capability to optimize and tune. And that's the advantage of the AMD EPYC hardware. But then it also does require some knowledge about how do you optimize your application for this hardware. So not to scare everybody, but it can be that you port your code and you don't even notice. It could be that you might want to take advantage of the architecture and do some optimization. And we have webinars related to that and workshops on optimizing for AMD. So take a look at our catalog and see if one of those can help you figure out. And if not, reach out to the support group. Our user services people are available and ready to help out. A couple of new feature projects that we're working on is something called composable systems. The idea is you're running a job and you need more resources out in the cloud. And so the composable systems will allow you to build your own system based on cyber infrastructure resources that are distributed. And this is a new concept. They've just finished year 1 where they're now moving into working with some early users, and next year it'll be even more open. But if you're interested, get in touch with the Expanse team and we'll talk to you about whether or not you might be able to use this. And then another project that's in progress is integration with the public cloud. And the vision here is when you submit a job to the Slurm batch scheduler, and I'll talk about what that is in a moment, but when you submit a job to run, the system might be busy and you might have some allocations out on Azure or AWS or Google Cloud. And so you might add an option in, hey, if available and it's faster, run my job out and use my cloud computing resources, and you'll not even really notice that that's happening. So it'd be a seamless integration and capability to spawn jobs to the cloud and or to just run them on Expanse and support both. And this one is another new project in progress that probably next year we'll be doing some early user testing on that. Okay, so let's just get back to a generic HPC system called Expanse. So you need to be able to log on. And if you haven't, then we have some tools to and tutorials to help you learn how to do that. We do single sign-on through the Exceed user portal. So your authentication and your credentials come from the Exceed user portal. And you can log on just like you do from any other shell window. You can log on using SSH. To note though, the CPU and GPU resources are allocated separately. And so the same, and the logons look the same though, but if you want to run on GPU, you need to apply for and have allocations that are separate from CPU, and often people forget. So make sure you're aware of that when you apply for allocations or you're working on a project, and make sure you have the right project account. To log on, the domain name is login.expanse.scsc.edu, and then you'll secure shell in SSH. And if you don't know much about that, there's some great tutorials out there, and we have a user tutorial to help you get started on that. But you have to put in your account information and log in. And you'll be assigned to one of 2 login nodes, login 0 and login 1. So I'll show you a diagram explaining that in a moment. So SSH keys are important to be able to have authorized access. So we're using RSA, ECDSA, and ED2 5519 keys and more, probably tons more. But if you use your SSH and you install an updated version on your laptop, you'll be generating keys that are acceptable. And you need to have a strong passphrase on the private key. And we're tightening that down more and more and going to two-factor authentication. So over time that will change. You can use something called SSH agent forwarding to avoid having to repeatedly type that long private key password. And we have a little repository where we have some mini tutorials on that. And what you can do is you generate your key, and then using SSH agent, you enable it to be forwarded to the machine you want to log on. You run it once, use your password, get the key over on the remote machine, and then ever after that, unless your time, it's allowed, you have to set a time limit on it, but then you can have passwordless, basically, authentication. But we want you doing it with SSH agent. So also this little caveat here, if you like to use config and you like to use keep alive and things like that, we check how often you're doing that and don't allow multiple pings, or it would be considered a denial of service attack. So you can use these capabilities, just use them carefully. And we also have a webinar that was given last spring on indispensable security, given by Scott Sakai. And we'll do another one next year to update it. All right, once you want to get on, what are you getting on to? So you're typically on a client like your laptop or a local cluster or workstation, and then you use SSH and you log on. So this lower blue row here these are all the clients, and through some network, you come in and you log on to Expanse, login.expanse.scsc.edu. And when you log on, you're not logging on to those big racks that I showed you in the cluster. Those are behind a sort of a gateway and a switching system that controls and gives you access to these compute nodes when you're ready for them. In the meantime, everybody comes onto the login nodes, and most HPC systems have multiple login nodes, because when you have 1,000 people logging on, trying to set up their jobs, compile and move data, you need a lot of capability just to let people get onto the system. And so you log on to the login node. It'll be either login 0 or login 1 or login 2, depending on the system you're at. For Expanse, it's login 1 and login 2. You'll have the same file system when you do log on, the same view into it. And as part of our Expanse 101 tutorial that you can go look at online, you can copy and paste some of the commands and see. Hello, somebody's got their mic on. All right, so when you actually do log on, SSH-L, your username, and login, you'll come into some kind of welcome message. You kind of call the message of the day. And you can figure out who you are and where you are in the directory system. Use the login nodes properly. There's only so many resources on the login nodes. They're not meant for running parallel jobs. They're not meant for testing parallel jobs. They're not meant for high compute intensive work of any kind. They're not meant for launching Jupyter notebooks or running MATLAB or RStudio. We want you to do those on interactive nodes, and I'll show you how to do that. They're meant just for people to get on and do a little bit of compiling, but if you have a big compile job, you really should do it on an interactive node. There's times when you'll be working and all of a sudden, just to do a file listing, it's taking a minute, and you look and run a little command called top and discover somebody's running a parallel code. And if the sysadmin people notice that, they'll kill that job. So don't use it for anything computationally. They're not the same as the batch nodes, and I hope by the end of today, that's pretty clear. Okay, so let's look at modules. So once you log on, the commands I showed you that I ran here, who am I, PWD, when you log on to any system, you have some default software capability, and we call that your environment. You can do listings, you can transfer, you can do moving, the basic Unix commands. And if you're new to Unix, we have a tutorial with basic commands that we think you need to know to work on an HPC system. But the modules are what give you that basic capability, and it's a way for you to add to your environment by loading the modules that are supported by this system, and it goes into your shell environment. They're very powerful. You can dynamically modify your shell environment for your application, not my application, not the other 15,000 users that are on the system, but your application. So for example, if you're compiling all of your code with the Intel compiler, you really don't need anything connected with the PGI compiler. You want to know all the software that's available for the Intel compiler. So you load in the Intel compiler module, and then that gives you access to any of the software installed by our sysadmin people that are running using Intel in the Intel environment. So it's very powerful and customizable. On the other side, though, you have to learn how to use modules. There's a bit of a learning curve, but once you get it, it's not too awful. But the reason you're motivated to do it is you then come up with a list of modules, you load them for your application, and your application will run the way you expect it to run. And also all the paths and the versions are maintained and updated by the systems people. So you need to load the scheduler like the Slurm, the Slurm scheduler. Typically that comes with your default environment, unless you've made changes, like you might want to restart and purge everything, start over, then you have to remember to load the Slurm module. You won't see all available modules as was on Comet, for example. You will see modules that are related to the modules that you've already loaded in. That's where some of that learning curve is. You have to decide what module path you need to go on, and you may have to test and debug several module configurations for your application. You can figure out what is out there using Module Spider, and it will go and see, for example, if you want to know all Amber, it will give you all the Ambers that are out there, not just the one maybe you're interested in Amber that's compiled with the Intel compiler. So you use Module Spider to get an idea of what's there, and it might inform you, oh, okay, I want this because it's only this one application I need is only compiled and working on Expanse using the AOCC compiler. Well, then I'll load the module AOCC and start debugging my code and compiling my code to work with that. So there's a refactoring kind of process that you go through as you nail down the modules.
Mary, we have questions, a quick question about the login. Login is asking for verification code. How do they get that?
The login is asking for, well, if you don't have your that's usually your password, or it's looking for an SSH key. So let's address that at the end, and then we can identify a couple of tutorials to help with that.
I'll make note of that.
Thanks. Yeah. Okay, so anyway, you can use Module Spider, and the module paths will be different for CPU and GPU nodes. So you need to know which one you're on. If you're on CPU, load the CPU. If you're on GPU, load the GPU module. Here are some basic examples for module commands. You can list the modules that are currently in your environment. You can look at the modules that are available. This one I cut down. Snip means I've taken out like 50 lines of code, but it does show you the information that you need. And here are some more popular commands. And all of these are in the Expanse 101 tutorial, where you can cut and paste and use the examples I'm showing you. Add modules, calls to your environment, and batch scripts. All of our examples show how to do that. And so if you want, for example, information about a module like CMake, you can do module show, and it tells you where everything's located and a lot of environment variable information. Once you've loaded some modules, you want to make sure it's in your path. So you can check for it by looking at your current path. Make sure if there's a library path variable that you need, make sure it's loaded in there. So that's how you check that it's in there. If you can't find all the modules, sometimes when you're moving and switching and swapping modules, things get the path for the system, the Luau system to trace through, it gets confused. So you just want to restart. So you can source this script called modules.shell and start again. It kind of cleans everything up, like picking up all the paper off the ground after you've written several versions of a draft. So accounts are important. You might have access to multiple projects, and you need to make sure you're using the allocation project ID for the project that you're working on. I'll show you an example. You should verify what your projects are when you log on. I'll show you how to do that. And make sure that you have to include the project in the SBatch that's different from Comet. And when you use SRun for interactive, you also have to use the project ID. Here's an example. We have a script called Expanse Client, and it can print out all the projects that you're on for CPU and GPU. But you have to load the SDSC module and run Expanse Client User. And for example, I'm on 4 projects here, and it tells me what I have available. And that's how you'll know which project ID to use for the project you're working on. Charging, 1 CPU core is determined to be 2 gigabytes of data for 1 hour. So make sure you're aware of how many resources you're asking for. Each node has 128 cores. So if you ask for a full node, you're going to get charged for 128 cores if you use it for an hour, for example. So if you're willing to share, then pick a partition that allows for sharing. And I'll show you that in a moment. The minimum charge for any job is 1 SU. So if you're doing some kind of scaling study, try and make sure you're doing those intelligently, or you'll use up all your allocation. And there's more information in our user guide. So now let's look at how to compile and link your codes. We support a large number of compilers on Expanse. They're all described in detail in the user guide and in the tutorial, and I'll go through them quickly. We support GNU Intel AOCC on CPU and multiple MPI implementations that should be familiar to you. A lot of our applications are built with GCC and they run fine. So make sure you know which compiler you want to work with. You don't necessarily need these other compilers here, but you probably need to test to figure out which one. We have support for AVX2, advanced vector extensions. On the GPU devices, we have GNU Intel and PGI compilers. And the login nodes note are not the same as the CPU and GPU nodes are different. So you need to make sure you're aware of what system you're on. The AOCC compilers, I'll just show you a pattern we've got in our user guides and the tutorial that lists for each of the compilers. There's a table you can find that tells you the primary languages and then the compiler command to use for serial or MPI, OpenMP, and MPI plus OpenMP hybrid. And the same for the CUDA. And then we tell you which module to load. And then there's always a way to get helpful information. So typically you want to make sure you have the right modules loaded. If you don't, you can start all over by purging the modules, listing them, and then loading each of the modules that you want. You can do it all in one line, by the way, but I keep it this way to make it clear. And then check your modules. And I wanted AOCC, so I'm happy about that. The other way to do it is if I currently have this list of modules shown in line 3, the blue line, then you can swap. Everything looked fine, except I don't want to use Intel. I want to use AOCC. So I use a command called module swap Intel to AOCC, and it had to go and check and support bring in a new OpenMPI module. And now I have an AOC module environment, and now I can go on and compile. And so it's the same for Intel, and it's the same for PGI. For Intel, if you want to make sure you're getting the AVX2 features or the Intel Math Kernel Library, be sure to put in the right arguments. PGI compiler is very similar. And then PGI is only on the GPU, so make sure you're on a GPU so you can compile and run. And the GNU compiler, good old GNU. Again, sometimes applications run more effectively and efficiently using the GNU compiler, so don't rule it out. Now, the rest of my talk, we're getting through the halfway point of my talk. I'll go over how to run jobs, and then I have several examples. I don't do them all, but they're all part of the GitHub repo, simple example that runs, so you can get started on running simple jobs and then build up your advanced environment. So we won't go through all of those today. But let's look at running jobs. Take a moment to think about what's the difference between the two key parallel models, which is distributed memory and shared memory. In distributed memory, you think of 5 workstations on your desktop, and they're connected by the some kind of networking. And to share data, you have to exchange data between the different physical pieces of hardware. And that's distributed memory. And it has to have some way of sending the data. And we call that message passing, MPI message passing interface. And so if you have a job that needs to go to multiple scalable compute units, then you're going to have to send data, and that can cost you time. So your goal is to try and keep your job on one node. And so shared memory, you might like the AMD EPYC as a shared memory model. You have a bunch of CPUs that can do some work. They each might have their own local data, and they have some kind of local interconnect, and they can all access and read from this local memory area. GPUs are good because they have a shared memory model. So you can get all your computing done without having to leave and send data off of your node. So some jobs, a lot of those will fit on the Comet nodes, and that's designed with that intent. So they all share memory. So where's your data going, and how are you going to parallelize the computation that you're doing? So running jobs, when we get to talking about batch mode, you'll submit jobs to that gateway, that batch. It's the Slurm server that decides which of the nodes you're going to run your job on, depending on how you're defining it. Computationally intensive jobs should not be run on the login node. We have limits on the number of jobs you can queue. You can read about all that. If you need to extend that, if you need to go beyond the limits, get in touch with the user support people. They'll help you figure out a better way to do what you're trying to do, or help you get permission to do what you need to do. All right, so running jobs, there's 2 primary ways. One is a batch job, the other one is an interactive job, and I'll go through those in detail. Batch jobs, you submit jobs to the Slurm scheduler, and you have to fill out some basic information. It just looks like a Unix shell script with some special keywords in it. And I'll show you examples. In interactive jobs, you use the srun command, and this will actually log you physically onto a compute node where you can do things interactively. The Slurm Resource Manager is the simple Linux utility for resource management. And again, there's that cluster diagram I showed you earlier, where you log on, you're on the login node, and you'll run a command to submit a job to the Slurm scheduler system. And it has a lot of features in it, and there's separate commands you would use to interact with it, but it decides which of these thousands of nodes that you need to use based on what you put into your script, and then manages it, launches your jobs, tracks output, and when the job is done, gives you a message and gives you all the output that might have been generated from your job. Very powerful. There's different, what we call partitions, compute shared, GPU shared, and these are just ways for us to allocate, charge you SUs, and it differs depending on which partition you're trying to use, and there's different constraints on how many hours you can run, etc. If you're confused about that, again, reach out to our user services group. You submit jobs using the sbatch command. So, and that's that script. And when you do submit it successfully, you'll get a job ID. If there's something wrong with your script, the scheduler will give you an error message, and you can go back and fix typos or whatever. You can check your job using the SQ command and your user ID, and it'll tell you if your job is pending or running. And you just keep monitoring your job until you see it's running, and then looking for when it's done, or looking for output or whatever. And when you want to, if you need to cancel it, cancel. There's many other commands. I just don't have time to go through them all. This is an example of a batch script showing it's a bash shell script. You can use other shell scripts. The pound sbatch is a keyword recognized by the Slurm system, where you give it particular information, the job name, where you want your output to go. %J is the job ID, %N is the job name you just defined, what partition you want, and more, and then your account allocation, how long you want this to run. Here, I'm just printing out my user environment, so I only need a minute. That also means it'll go more quickly because it's backfilled. And here's the output. I get an output with the name of my job, the job ID, and the .out, and I'm combining input standard out and standard error, and it prints out my module information. It's nice to have something like this that when you're having trouble getting things to run, if you've run this 100 times and you try to run it again and it doesn't, then there's something else going on than your new code, for example. It's like Hello World is very important for debugging all the layers of systems that you go through. So another area is interactive HPC computing. Right now I'm doing some interactive computing and running multiple applications on my laptop. And so from a computer science standpoint, that's interactive. I interact with my PowerPoint and you're interacting with Windows and mail and terminals. That's all parallel computing in a sense. But for HPC, it's a little bit different. What we define as interactive HPC is when in real time, you're on a compute node and you're doing inputs and interacting with an application on that compute node. It's an evolving concept that's emerging as pretty important, especially for things like Jupyter Notebook or running MATLAB and RStudio, which we support on Expanse, and I'll talk about it briefly. So interactive jobs, you need to run a particular command to get a CPU node. You wait until the Slurm scheduler finds a node for you that meets your requirements as defined in this srun command. And now I'm on it. I'm no longer on login 01. I'm on expanse-9-55. I own a node. It's all mine, or at least one core on that node if I chose a shared partition. Debug is a special quick turnaround partition that's good to use for early development. And so I'm looking at my modules and thinking, are these the ones I want? I don't quite think so, but it's a safe thing to do, which is to purge all the modules and do something called module restore. Whatever module environment you had on the login one does not necessarily, and most likely won't carry over. So start again, purge, restore, and then start building the modules that you want for every application. And if you do this, you'll have much more success. Okay, so this is a GPU. It's very similar. If you want to know if you're on a GPU, run the NVIDIA-SMI and it will tell you. Okay, so we have a couple of applications, like I said, that are interactive. A really popular one these days is the Jupyter Notebooks, which we've been developing and running a project called the Satellite Reverse Proxy Service, where we're helping you launch secure notebooks. By default, a Jupyter Notebook launches and runs on your browser using HTTP. And we're giving you a client that will allow you to run it using HTTPS. We view that Jupyter Notebook URL as a password, so you don't want to give it away. It gets you right onto your Expanse user directories. And so we're trying to help people learn to do this better. I'll put up a link. We have tutorials for this, but it's interactive computing. You launch a notebook and you're running jobs interactively. Satellite will tell you when it's getting launched and give you your browser, which is looking right at your files on Expanse. And you want to make sure you have that little lock icon, which protects your work, your notebook, our system, your accounts. And the Expanse User Portal is not only a user portal, but we're enabling several interactive services, including Jupyter Notebooks, Jupyter Lab, and MATLAB, and RStudio. And you can get to this through the Exceed User Portal account. So if you're a command line programmer like me, you're happy working with this slide that shows you you're on the command line, you're running a bunch of commands, you're launching Galileo, and that may be the model that you need to work in, but you also might prefer to come in through a more customized softer user environment. So check out the portal too. We have access to the same Galileo client, and it's secure access, and it has other features. Okay, so data management. This is really an important concept that the data systems on Expanse are different. So you have a home directory, which you see when you log in. You have high speed, high petabyte storage, the Lustre file system. And then you also have, when you get your own interactive node, you have some local node called Scratch. And you have to decide where you want your data to be. And moving your data from Lustre, for example, to the projects directory so you can run your Jupyter Notebook properly, there's some complexity there. And we have a webinar next month on data management, and I hope you guys come to that. I don't have a lot of time to go through it in detail, but the basics are here. This is how you work when you're on an interactive node. And then the Lustre file system, you have to be able to move your data, and you can see the Lustre file system, but you might be using the data from Lustre, or you might need to move it and stage it onto a different workspace. It depends on your application. What we see is with a lot of machine learning neural networks, a lot of file IO for that does cause some difficulty. So please get in touch with us so we can help you figure out maybe the best way to do large file IO during your application. And then we have Globus endpoints and data movers, and this is a great way to move data from remote, far away points like Amazon S3 buckets or some remote system back at your university, and you need to get data. You want to learn about the Globus endpoints, and we'll address that in more detail next month. Okay, now we're on to hands-on examples. Yay! So at this point, I'm going to mainly go through the MPI, but we have all these examples as part of the GitHub repository tutorial, and you can get these working. So there are a lot of examples in our tutorial, and it's always changing. So you want to be able to compile your example. For example, this is Expanse 101 MPI, and you want to look at your modules, and you want to use MPI F90 if it's Fortran code. We have a hello MPI.c as an example, and make sure the job is ready to go and submit a batch script. So let's look at this in more detail. This is the basics with all the basic MPI stuff, which I won't go through. And so you want to make sure, for all of our examples, we have a readme.txt file that tells you what modules you need, how to compile, how to run using the batch script, and also how to get onto a partition node. So here we've compiled successfully by getting the right modules. And so here's an example of the batch script that I showed you an example of earlier. Here we're building the environment, and here I'm using srun. I submit that to the scheduler, and the scheduler eventually gets a job submitted and gets a allocation, runs the job, and when it's done, I have an output file, and it prints out my 135 hello worlds. And notice those are not, yes?
Yeah, 5 minutes.
Okay, great. Well, we're just about in. If you're on an interactive node, you do the same thing. What's nice about this is you can run your code from the command line, and there's my output. And so these are really pretty much OpenMP. I'll just skip over to the final comments. And GPU is very similar. You have to log on to a GPU interactive node by using, if you're going to do interactive, or with your SBatch, make sure you're using a partition that's GPU shared. Everything else is very similar. So here we have a Laplace example that you guys are welcome to try. Get the interactive node, make sure I'm on NVIDIA, and then here's the similar commands. When you compile this example, you'll get some output, a lot of output. Just, it's typical and it's normal. Then you should, once you do get the compiling to work, then you can submit the batch script. But this should work out of the box for all of you on our GPU nodes. Okay, final comments. Yes, you're correct. It can be a little complicated. There's a lot of material we just covered. So let me get out of, escape out of this, end the show. So I've stopped sharing screen. I don't think I need to share anymore because we are getting to the end. So, but just in summary, it's kind of a complicated environment that we're in, and which is why we do all these basic webinars and why I've put together this webinar. So feel free to contact us with questions. What I forgot to show, and it's in the talk, is, let me share again so I can show you. We do have a slide in here that is all of our resources. Again, we have a user guide, and we have all of this Expanse is in our training repository, and also we have a Expanse 101 self-paced tutorial that you can go to. And with that, thank you for your time. I think we have a minute or two for a couple of questions.
Yeah, Mary, I took down some questions that were in the chat. So
Okay,
one of it
great.
was on one of your earlier slides is someone had asked, like, are only people who work on the 4 topics mentioned on your earlier slide can get long-term allocations on Expanse, or other topics are also accepted?
No, you can, no, that was just an example. And I think what you mean by the 4 topics, you mean like the scientific domains?
I'll let her respond if she wants to unmute. I'm not sure which slide it was when she kind of.
That's a good question, Nadia. So what do you mean by the 4 topics? She might not be here. I'm going to guess that what she meant was, because I don't have time to go look at the slide number. You can get allocations for any valid scientific domain supported by the NSF or your university, Department of Energy, Department of Defense. I mean, there's really no limit. You can, if you're a researcher, you are eligible to use these resources. And what you would do is vet that and work it out with allocations people on Exceed or even on Expanse. And we can, there is even a tutorial coming up on Exceed about how to get an allocation. So look for those resources and they'll teach you and help guide you. And if you're still confused, get in touch with us and we'll direct you. Anybody doing research in a research institution is most likely working on something that can be as eligible for using on Expanse.
Thanks, Mary. So there's a couple more questions. So I'm going to revisit the login question. Some people were trying to log in and it was asking for a verification code. How is one supposed to get that?
Yeah, I really need to see an example of that. The verification code usually means that it's not asking you for a password, so you don't have your SSH installed properly on your laptop. And so you want to go, I don't know what kind of system you're working on, but if you don't have if you're on Unix, for example, Linux, you have a .ssh directory, and in it you generate a public-private key pair, and then SSH is allowed to run. So you may not have SSH configured properly. And if you still are having trouble, send an email to help@exceed.org and it'll get, because it's Expanse related, it'll get redirected to our user support people and you'll hear back from them very quickly.
I found the problem. The problem was the username was misspelled. Once I spelled the username correctly, then it asked me for the password, then it worked fine.
Oh, okay, great.
Thanks for
Thank you for the clarification.
Yeah. Another question was, why can I not go to the Expanse by entering, GSI SSH Expanse at Exceed portal? It showed permission denied.
That is a question for user support people. That I think, I'm not sure how supported that is, and Scott's not around, our security guy. I would like you to submit that question to help@exceed.org because I don't know the answer to that. It's a great question. And I come from the GSI community, long-term grid forum person, but I don't use it, so I'm not familiar with what that issue might be. So yeah.
Okay. So next question is, can you briefly describe CPU and GPU memory? And we have a couple others, so.
CPU and GPU memory. That gets down to the heart of architecture. So CPU is, memory is memory, but on the CPU, you tend to have the compute core and then some different levels of cache associated with the CPU. You'll have level 1, level 2, level 3, and then you have some external cache that's larger. Level 1, level 2, level 3 are larger and larger packets of data. And the level 1 is faster to move data right into the CPU core. And so the different memories are located spatially farther away from where the work is getting done. And so it takes longer to move your data in and out. And what they do is have these different levels of cache so you can stage data. You get, 1,000 bytes of data ready in level 3 to go down to 100 bytes of data in level 2 to go down to 10 bytes of data in level 1. And then each time you do let's say a binary operation of A equals B plus C, you move B and C in and you calculate A. So it's where you move in the data and how much can you move at one time. And in GPU, the core compute elements are closer to the data, but they're smaller. And there's a lot of different, it's still got the sense of a local cache, but it's got a different term. But you have local, each GPU core, and it's a different core than what we're talking about on CPU. You have small cores that do, they're pretty much designed to do atomic computations, and they're small memory, but you're only going to move in if you're doing A plus B, A equals B plus C, you're going to move in A, B, and C, and that's the most memory you need. Maybe double precision these days because it used to be single, but there's still some GPUs out there optimized for integer arithmetic. But you get your data on there, you do that little tiny calculation, and then you move it off and move in some new data. So they have smaller data per GPU core, but there's a lot more GPU cores, tens and tens of thousands of cores. Does that answer your question? And then GPU still has to be able to access some larger memory where like your whole matrix is stored, and you have to typically move that matrix from the CPU down to the GPU if you're accelerating your calculation with GPU.
Thanks, Mary. Hope that answered your question. Next
Hope
question. Thanks. One question is regarding max runtime. The portal says Expanse supports long running jobs. Runtimes can be extended to 1 week. Can you comment? Thank you.
I can comment. The comment's not designed for week-long jobs. It's designed for 48-hour jobs on purpose with intent. That's the long tail of science. Most people in the community that Expanse was designed for only require a few thousand cores and a certain limitation of memory, and should be done within 48 hours. So if you need to run longer, then you interact with our team. But it's the philosophy of how Comet was designed. If you need more time regularly, you should be on a bigger system like Frontier or some other larger scale system with hundreds of thousands of nodes, right? So exascale systems. So you might not belong on Comet. So if you're in that area where you think you're going to go there someday, learn on Expanse how far you can go, but then get permission to run a week-long job now and then. Certainly if it's COVID related or disaster response related, then we do have teams that work with people who are in that area and reach out to us. But in either case, if you feel like your application needs to run a week and you ended up getting Expanse allocations and now you're realizing that might not work with the user services group, and maybe you need to move to another system and we can help facilitate that.
Right. And then another question. You have a lot of questions. So
if I can stay a little bit longer.
Okay, we have some time. We have like 4 minutes.
Yeah.
If we're using cloud computing for educational purposes, for example, Jupyter Notebook for a class, do we need to create a class user? You said the Jupyter counted as your user account.
Using cloud computing on Expanse, you wouldn't be doing that on Expanse right now. A couple of comments. Creating resources for a class is tricky, and you have to either have a community account and some kind of community portal gateway, so you can have multiple users running off that one community account. We have to decide what your application is. If it's a class at UCSD, they have a system that's designed for students and classes with their own cluster that we maintain for them, but you would get it through that. If you want to create a class account on Expanse, we do have training allocations. So first thing is you look at the Exceed allocation website and write up an allocation where you might get accounts created for each of your students. You might ask for an account that's called Training 101, 102, 103. We do our training that way. So what you want to do is look at the education allocation and then talk to us about maybe the best way to apply for that. But you can do classes. It would generally not be under one account and everybody's coming onto your Jupyter notebook. We don't like that. That's not secure enough for us. Like you write a notebook, launch it, and give everybody that URL. We monitor for that and you would get shut down. But if you want each student to work on a Jupyter notebook, we're happy to help you get a training account. So quick turnaround on that, just a few weeks. Sooner if you have a class coming up and you've got allocations and you need to get rolling. But we can do both ways.
Awesome.
Good question. Yeah.
Thank you. And then as commented on, is the passcode number for two-factor authentication using Duo Mobile? The passcode number.
Passcode. So for doing two-factor authentication and you set up Duo, it will, if you're using the Exceed portal and you're authenticating with their two-factor, Duo will automatically take care of that for you. So two-factor authentication on Expanse is still in the early development stage, like early user testing, and I really don't know what the details are. And unfortunately, there's nobody here working on that project. Are you using Duo right now to
Sorry, Mary.
authenticate?
Sorry, that was just a suggestion to someone else's problem that he was.
Oh,
commenting,
okay.
or she
All
was
right.
commenting.
Okay.
Yes.
All right. Great.
I apologize for
All
that.
right.
And then someone asked about a question regarding, I have been using SUC to access Comet. Will this work for Expanse?
They've been using what?
Comet, using STC to access Comet. Will this work for Expanse?
I've been using, if you were running jobs on Comet in the recent year or two, you should have been getting far more emails than you might like on transitioning to Expanse, getting your allocations migrated to Expanse. Comet is shut down now, and not sure all the files are there anymore. So if you have files on Comet, send a note to help@exceed.org about that. Whatever you were doing on Comet, we're finding most users' applications are transferring, compiling, and running fine. Not noticing a lot of migration issues because we still support most of the compilers from Comet. The new one is the AOCC, and there's conditions where you might want to use that compiler. But you should be able to just get on Expanse, compile, and run.
I posted on, sorry, Mary, go ahead.
That's okay, unless you're using something like the Intel MKL library, then you might need to change your compilation scripts, like for word paths to different things, but it should work fine. I hope that answers your question.
I also posted on the chat the Comet to Expanse transition tutorial.
Oh, thank you.
So
yes.
you can visit that as well.
Yes.
And with that, that's the last questions that I kind of tracked.
All right. Well, with that,
yeah, thank you everyone for joining us. Next month, we'll have data management on file systems on Expanse. So please be sure to register and we'll send you all the details you need then. Thanks,
can you put that link in the chat?
Oh,
thanks, guys. Thanks for coming. We appreciate all your time.
Let's see, I hope I get there. I'll stop.
Great, thank you.
Thank you.